Hi, my name is Radu. Welcome to my presentation about the complexity of immanence. Let me start with a micro summary of this talk. In a nutshell, immanents are a particular class of matrix functionals. This class contains the determinant, which we all know, and the permanent, which you may have encountered as well. These are extreme cases of immanence, but there are more. Every partition of a number n defines a particular immanent for n by n matrices. This talk will address two questions. Firstly, which immanents are easy or hard to compute? And secondly, why should you even care? So let's start. The story begins with a determinant. Determinants are important in linear algebra, geometry, combinatorics, and many other areas. Determinants are also interesting from an algorithmic perspective because some problems can be solved by interesting reductions to determinants. To be honest, I'm still fascinated by the fact that determinants can be computed efficiently. To understand why this could be fascinating, let's look at a way of computing determinants inefficiently, the so-called Leibniz expansion. In the Leibniz expansion, you sum over all permutations of the numbers 1 up to n. And for each permutation pi, you take its sign and multiply it with the product over n matrix entries that are selected by pi. Recall that the sign of pi is plus or minus 1, depending on whether pi has an even or odd number of cycles. So in this Leibniz expansion, you're summing over n factorial terms, which would generally be hard, but of course, this equality here saves the day. Because as we all know, determinants can be computed in polynomial time. For example, Gaussian elimination can do it in O of n cubed operations. There is also a way of reducing determinants to matrix multiplication. This gives you O of n to the omega operations. And there are also nice combinatorial and division-free algorithms for computing determinants. The permanent looks misleadingly similar. You can again define it by a sum over all permutations of the numbers 1 up to n, and again each term takes the product of n matrix entries depending on pi, but now we replace the sign of the permutation by nothing, that is, by 1. There is a nice graph-theoretic interpretation of the permanent of A. It just counts perfect matchings in bipartite graphs, and this seems to be hard. That is, we don't know any polynomial time algorithm for evaluating permanence. Essentially, the best we know is Reiser's formula, a nice application of the inclusion-exclusion principle, but this also just brings the complexity down from factorial to merely exponential. And the related formula by Glynn essentially gives the same time. Such super polynomial running times are to be expected, however, because a classical result by Valiant establishes the permanent to be hard for sharp p, which is the equivalent of NP in counting complexity, and hard for VNP, which is the equivalent of NP in algebraic complexity. A 2 to the omega n lower bound also follows under the exponential time hypothesis. So conditional lower bounds from complexity theory suggest that the permanent really is harder than the determinant. And people have also tried to prove unconditional lower bounds. More precisely, there is an algebraic variant of the P versus NP question, namely the permanent versus determinant problem. This problem asks about the minimum size of a determinantal projection of the permanent. What does that mean? For fixed n, let's consider the matrix with indeterminate xij at position ij. These are n-square indeterminates. The determinant and the permanent of this matrix are multilinear polynomials of degree n in these n-square indeterminates. A determinantal projection of the n-permanent now is just a matrix of affine linear forms in these n-square indeterminates, and the determinant of this matrix, which may be much larger than n by n, by the way, should equal the permanent. Here are two examples. And in general, a determinant of size 2 to the n minus 1 suffices for the n-permanent. But can we prove a lower bound? This would essentially prove p not equals np in algebraic complexity. And all we know so far is a lower bound of n square by Mignon-Resser. So a permanent with side length n needs a determinant with side length n square. In this talk, we will try to get a better understanding of permanents and determinants by realizing that they're actually just two extreme members of a large family. And maybe understanding that family will help us understand the tricky relationship between its extreme members. This leads us to the so-called immanents. As you can see, the determinant and permanent are defined in a similar way. They only differ in how we weight permutations. Here we have the sign function, and here we have the trivial all-one function. So why don't we just look at general functions for weighting permutations and study the objects that come out? Maybe the sign and the all-one function aren't that special in the end. So let's do the obvious thing, fix a function f from permutations into some field, and then define a determinant permanentish object where permutations are weighted by f. This is called the f-immanent. It turns out now that this definition is a bit too permissive, and we want our immanents to behave a bit more nicely. Namely, if we permute the rows and columns of A by the same permutation, then the immanent should not change. This sanity requirement means that we cannot choose arbitrary functions f, but only so-called class functions of Sn. These are those weighting functions that depend only on the cycle format of their input permutation. The cycle format of a permutation pi in Sn is the partition of the number n that is given by the cycle lengths of pi. Class functions form a vector space under scalar multiplication and pointwise addition. The dimension of the space is equal to the number of partitions of n, that is the nth Bell number. And being a vector space, class functions of course admit a basis. And there is a particularly interesting basis, which is given by the so-called irreducible characters of Sn. Very roughly speaking, this is a bit like the Fourier basis for class functions. This basis will be important for us, so let's have a closer look. For an example, let's fix n to be 6, so we look at 6 by 6 matrices and the group S6. This here is a character table. Each column corresponds to one of 11 possible cycle formats. The numbers in this row just count how many permutations have a given format, and a class function can now be specified by a row vector. The irreducible characters of S6 are 11 particular row vectors, which are again indexed by partitions, and these row vectors span the entire space of class functions. We draw the partitions that index irreducible characters as Young diagrams. For partition lambda of n, such a diagram has n boxes. The parts of the partition are sorted, and each part corresponds to one row. So we have a horizontal line of n boxes, a vertical line of n boxes, and all kinds of partitions in between. We will later see where these integers in the table come from, but you can already see that the sign and trivial character are extreme cases, and they give us the determinant and permanent. But there are 9 other irreducible characters, so 9 other immanents that we can look at. So let's get back to the main story. We're going to restrict the function f in the definition of our immanence to be an irreducible character. So for any partition lambda, we define the lambda immanent to be the immanent where permutations are weighted by the character chi lambda that corresponds to the partition lambda. This gives us a spectrum of matrix functionals, so-called character immanents, that live between the permanent and determinant. You might wonder why we restrict from general class functions to characters. If you recall, when we restricted to class functions, we had no other choice. But the reason for restricting further to character immanents is just that this is how immanents are usually defined in algebra and combinatorics, and in particular, all known algorithms and complexity results address only such character immanents. So let's talk about complexity. To make sense, we will need to look at families of immanents, that is, families of partitions. Let lambda be some family of partitions. We define the problem im lambda as follows. As input, you get a partition lambda from your family of some number n, and you also get an n by n matrix A. The task is then to just evaluate the lambda immanent of A. This collection of problems includes the determinant, which is easy to compute, and the permanent, which is hard, but more is known about immanence. And let's start with the algorithmic side. There is a particular parameter b. If this parameter is finite in lambda, then the immanent problem for lambda is polytime. This parameter b is defined in a really simple way. For any partition lambda, just look at the Young diagram of lambda and just count how many boxes are not in the first column. In other words, imagine you're paying for the boxes in lambda, but the first column is for free. And given a family of partitions, you just define its b-value to be the maximum taken over all the partitions in the family. Note that the partitions that define determinants, these vertical lines, have b-value 0. So as long as you're close to such partitions, you still get a polynomial time immanent. On the hardness side, some results extend the hardness of permanence. For example, there are hook immanents. They are defined by partitions that have one large block followed by blocks of size 1. So their Young diagrams look like hooks. Now, if you have a family of hooks in which the width grows polynomially, then the resulting immanents are known to be sharply hard. This was generalized later to partitions with a polynomially wide gap. That is, somewhere in your partitions, the difference between two consecutive rows should be at least polynomial. And at this point, it seemed reasonable to conjecture that immanents are hard for wide partitions. However, and possibly surprisingly, it was shown later that for partitions of width 2, you can already get hard immanents. So now it made sense to conjecture hardness for families where the algorithmic criterion on the left fails. That is, where the b-value of lambda is infinite. Some progress towards this was made. If you have such a family lambda with infinite b-value but constant width, then you get hard immanence. But the general conjecture remained unresolved. And in fact, there are even very simple special cases that couldn't be addressed before. For example, staircase partitions. These have unbounded width, so the bounded width result doesn't work. And they also don't have any wide gaps, so you don't get hardness from the gap-based result. In this talk, we settle the general conjecture. We show that any partition family with unbounded b-value gives sharp p-hard and VNP complete immanence. This completes the polynomial time solvable families exactly. And okay, there is a star here because there is some fine print that we need to discuss. So let's get into this. We say that a partition family lambda has growth f for some function f from n to n if the following holds. For any number n, you can find a partition lambda n in your family such that two things hold. Firstly, this partition has theta of n boxes, and secondly, its b-value is at least f of n. In other words, we can find partitions that have enough boxes outside of the first column, and furthermore, these partitions overall are neither too large nor too small. All of the hard families we considered before have polynomial growth. And we show that any family with polynomial growth gives hard immanence. But this result doesn't cover all families with unbounded b-value. For example, for some of these partition families, the b-value may grow slower than any polynomial. You can think, for example, of hooks that have logarithmic width. Such hooks actually give immanents that can be computed in quasi-polynomial time, and such problems fall into the blind spot between p and np. Fortunately, however, we can still talk about such classes using parameterized complexity. Assuming that fpt is not equal to sharp w1, we show that any family with unbounded growth induces an immanent that is not in P. The growth here may be arbitrarily slow, in particular sub-polynomial. If parameterized complexity is new to you, let me give you an extremely brief overview. Consider a parameterized version of the clique counting problem. You're given a graph G with n vertices and a number k, and you want to figure out how many k cliques there are in G. And let's assume that k is much smaller than n. Then you can solve this problem using brute force in n to the O of k time. And for constant k, this is polynomial time. Now, would it be possible to remove k from the exponent? This leads us to the concept of fixed parameter tractability. The k-clique problem would be fixed parameter tractable if it could be solved in time g of k times poly n for some computable function g that depends only on k. The statement that FPT is not equal to sharp W1 essentially means that such a nice k-clique algorithm won't happen. This, by the way, is also implied by the exponential time hypothesis. And there is also an algebraic variant of FPT and sharp W1, which was introduced recently by Blazer and Engels. So to summarize, if you believe that sharp p-hard problems are not polynomial time solvable, then the first result here is for you. Any partition family with polynomial growth gives immanence outside of P. If you believe the stronger assumption that sharp W1 hard problems are not fixed parameter tractable, then you can extend the hardness to any partition family of unbounded growth without having to care about polynomial bounds. How can we prove this? First, we need to understand the irreducible characters of Sn a bit better. A nice combinatorial formula will help us here, the Monaghan-Nakayama rule. Let's say we want to evaluate the irreducible character chi lambda at some cycle format rho. Lambda is shown as the gray diagram here, and rho is listed here. The first step is to pick some arbitrary part from rho, let's call it k, and then decompose rho as k followed by rho prime, which is just the remaining cycle format. The Monaghan-Nakayama rule now tells us that chi lambda at rho is equal to a particular sum. The terms in the sum correspond to so-called border strips of length k that can be peeled from the southeastern border of lambda. Border strips are connected shapes that don't contain any 2x2 squares, and after removing a strip, you should still have a valid partition left. The term corresponding to a strip is a particular sign, depending on the height of mu, times the value you get from recursively applying the rule. In this recursive application, you take the character for lambda with mu removed and evaluate it on the cycle format rho prime. And this will terminate at some point. You can also collect all the recursive choices into one combinatorial object, a so-called border strip tableau. The thing on the left is just a border strip tableau. Okay. This method will be used throughout our proofs. Now, let's consider a partition lambda with a large number of boxes outside of the first column. We will show that lambda contains at least one of two useful resources: a large staircase, which is a partition of the form shown above, or a large number of non-vanishing tetrominos, which are these four-box shapes here. Note that the vertical four-box line is not among the non-vanishing tetrominos, and this makes sense because it would otherwise allow us to prove that determinants are hard. We will need to formalize these resources a bit more. Given lambda, first peel the maximum number of dominoes from it, and let us write d of lambda for this maximum number. And here a domino is just a connected two-box strip, and peeling means the same peeling as in the Monaghan-Nakayama rule. After we've peeled these strips, the remainder of lambda will be a staircase. This staircase will be uniquely determined, it could also be empty, and we write w of lambda for its width. In the shape consisting of the peeled dominoes, we then try to peel non-vanishing tetrominos. For the disconnected ones, which consist of two dominoes, we adopt this convention that we want to peel the dominoes individually, but making sure that the locations of the connected components that we peel don't share any rows or columns. Then we write S of lambda for the maximum number of non-vanishing tetrominos that can be peeled this way. The quantities W, B, and S are connected. Essentially, any partition lambda satisfies at least one of the following. Either W of lambda is at least omega square root of B lambda. So if B is large, then there is a large staircase. Or S of lambda is at least omega B of lambda. So if B is large, then there are many non-vanishing tetrominos. This can be shown by an elementary but a bit tedious combinatorial argument, but it shows that indeed if B is large, then either W or S must be large. And then our proof, of course, proceeds by case distinction. If there is a large staircase in our partition, we reduce counting perfect matchings in a bipartite graph G, that is the permanent, to evaluating the lambda immanent. Firstly, this requires us to get rid of all the dominoes to expose the staircase. We can achieve this by padding, but showing that this works requires a non-trivial argument involving domino tilings, which is a bit surprising. And after we got rid of these dominoes, the part of lambda that remains is some staircase mu. And staircase characters have a very peculiar property. They vanish on any cycle format that contains an even cycle somewhere. We can use this property then to construct a graph H, such that the perfect matchings in G correspond to those cycle covers in H that don't vanish under the staircase character. And then overall, the lambda immanent of the adjacency matrix of H will essentially count perfect matchings in G. In the other case, we have a large number of non-vanishing tetrominos. Then we use a particular edge gadget that allows us to simulate an edge in a perfect matching. For each edge uv in G, we insert this gadget between u and v, and this gadget comes in 3 different states. All other states will cancel out in pairs due to this -1 edge weight in the middle. The blue state does not cover any of u or v, and this corresponds to not including uv into a matching. And the 2 green states cover both u and v. This corresponds to including uv into a matching. Each gadget in the blue not taken state needs a domino from lambda to work, and each gadget in the green taken state needs one non-vanishing tetromino to work. If lambda provides enough of these resources, then the lambda immanent of the resulting graph will again count perfect matchings in a bipartite graph, that is, solve the permanent. Okay, this essentially concludes my talk. To recap, we looked at the problem of evaluating immanence defined by families of irreducible characters. Such characters can be specified by partitions. It was known before that immanence can be evaluated in polynomial time if their defining partitions have a finite number of boxes outside of the first column. And now we know that in all other cases, subject to technical conditions, the problem is hard. This concludes a line of partial results on this problem. There are also some nice avenues for future research that arise from this work. Firstly, we can look at immanence modulo fixed primes. Then we can look at planar instances. Of course, there are also natural fine-grained complexity questions. And then we currently only have hardness for integer-valued matrices, but I would suspect that we can also prove it for 0, 1 matrices. Thank you for your attention.